partial correlation and regression coefficients part 1. Let us begin as usual with a 3 variable model given as yi is equal to beta 1 plus beta 2 x 2I plus beta 3 x 3I plus ui, where I runs from 1 to n. We already know that after estimating this model, we can decompose the total sum of squares into explained sum of squares and residual sum of squares. What we will do to begin with is, we will carry out this exercise in a stepwise manner, which will bring out the relation between simple, partial and multiple correlation coefficients. So, we look now at the stepwise build up of this decomposition of the total sum of squares. So, in step 1, what we do is, we regress y on simply one of the 2 explanatory variables, say x2. So, we write yi is equal to alpha 1 plus alpha 2 x 2I plus say vi, which is the random disturbance term. Now, from this simple regression, what we obtain is alpha 2 hat is given as summation yi x 2I divide summation x 2I square, and we find out this alpha 2 hat in order to get the explained sum of squares in stage 1, which is ESS step 1 or stage 1, is given as r square y 2 times summation yi square. So, that is the total sum of squares, and this is the square of the ordinary or simple correlation between the explained variable y and the regressor x2. So, that is in step 1 the explained sum of squares, where this r square will depend on alpha 2 hat. Similarly, the residual sum of squares in step 1 will be 1 minus r square y 2 summation yi square. So, at the end of step 1, we obtain explained sum of squares step 1 and residual sum of squares step 1. Together with that, we obtain the residual values y2. E y2 is the error when y is regressed on x2, and that is defined as yi minus alpha 2 hat x 2I, which is given as yi minus, substituting the value of alpha 2 hat, we have summation yi x 2I divide summation x 2I square into x 2I. And by now, viewers, you might have guessed that this is nothing but that part of y which does not contain x2. So, this is y and that part of y which is explained with the help of x2. So, the whole thing is pure y, that means y purged of the effect of x2. So, this is called pure y, and that will be used in the next stage. So, coming to stage 2 or step 2, we will now introduce the other variable x3. We already have x2 in the model, we will now introduce x3, but remember x3 and x2 are correlated. So, we need to purge x3 as well, we need to cleanse x3 of the effect of x2. So, what we do is, we introduce x3, we regress x3 on x2 to obtain the residual, that is E32, the residual obtained when x3 is regressed on x2, that is x3 minus summation x3I x2I divide x2I square times x2I. Step 2, what we obtain is explained sum of squares in step 2 is, please see that in step 1 this is the residual sum of squares which becomes the total sum of squares in step 2. So, this is 1 minus r square y2 summation yi square, that is the total sum of squares, and the explained part of it is r square y3 dot 2. First we had introduced x2 and then we had introduced x3. So, this is r square y on 3 purged of the effect of 2. So, this is the partial correlation between y and x3 keeping aside the effect of x2. So, that is called the partial correlation coefficient, and the residual sum of squares RSS 2 will be 1 minus r square y2 into summation yi square into 1 minus r square y3 dot 2, and this is actually equal to the final residual sum of squares. So, initial stage we introduce x2, we have explained and residual sum of squares. This residual sum of squares further decomposed into explained sum of squares and residual sum of squares. So, this is the net residual sum of squares. So, what we do is we write that explained sum of squares, this explained sum of squares is given as ESS1 plus ESS2, which is, if we substitute ESS1 and ESS2, then we get r square y2 plus 1 minus r square y2 into r square y3 dot 2 whole thing multiplied by summation yi square. But viewers, you already know that explained sum of squares in a multivariate model or multiple regression model is nothing but r square capital Y dot 23 times summation yi square. So, that is the multiple correlation coefficient, the square of that, or the coefficient of determination, that into yi square is one way of expressing the explained sum of squares, and the stepwise decomposition gives another way. So, if we simply strike out yi square from both sides, then we get a nice result, that is r square y dot 23 is equal to r square y2 plus 1 minus r square y2 into r square y3 dot 2. Notice that in this stepwise decomposition, first we had introduced x2 and then we had introduced x3. We can do a similar stepwise decomposition or stepwise build up by first introducing x3 and then introducing x2. So, that is what we will do in a few minutes from now. Let us look at an alternative way of stepwise build up. We can, in step 1, include only x3 and then we can introduce x2 in step 2. So, accordingly, the explained sum of squares will be the sum of ESS1 and ESS2. Here ESS1 is r square y3 because we had introduced x3. So, it is r square y3 summation yi square, and 1 minus r square y3 summation yi square is the residual sum of squares in step 1, which is further decomposed into explained sum of squares in step 2 given by r square y2 dot 3. So, that gives us the whole explained sum of squares, that is multiple correlation whole square r square y dot 2 3 times summation yi square. In other words, striking out the summation yi squares, we get r square y dot 2 3 equal to r square y3 plus 1 minus r square y3 times r square y2 dot 3, and therefore 1 minus r square y dot 2 3, which is the residual sum of squares after step 2 or the final residual sum of squares, comes out to be 1 minus r square y3 whole multiplied by 1 minus r square y2 dot 3. Or if you look at the earlier one, the earlier approach was to include first x2 and then x3, that would give us 1 minus r square y2, the residue from the first step, times 1 minus r square y3 dot 2 when 3 is included in the second step. After this, what we will look at is the partial and simple correlation coefficients and the relation between them. The partial correlation coefficient between y and x3 given x2 is nothing but the simple correlation between the residuals obtained when y is cleansed of 2 and x3 is also cleansed of x2. So, that is summation error y2 I, that means the residue when y is regressed on 2. So, y is cleansed of 2 and E32 I divided by the square root of their variances. Now, we have already defined these two. Specifically, we defined the error as EY2I is yi minus, this is the coefficient estimated, times x2i, and E32I is x3i minus again the coefficient from the regression of x3 on x2 times x2. So, if you multiply yi x3i, then yi x2i times x3 x2 divided by x2i square, and on the other hand yi x2i divide x2i square into x2i x3i, and finally minus and minus gives us plus, and this term that is summation yi x2i divided by x2i square, again summation yi x3i x2i divided by x2i square, which gives us a whole square times x2i square. So, if you see here, this summation x2i square and this whole square gets cancelled, and then it is easy to see that these two terms are the same with opposite signs, yi x2i, yi x2i, x2 x3, x2 x3 divided by x2i square, x2i square. So, these two terms also get cancelled and we are left with just two terms, summation yi x3i minus summation yi x2i times x3i x2i divided by summation x2i square. And so, if we just replace this numerator here, that is what we have done here, taken this expression and replaced it here on the numerator, whereas the denominator is much easier to explain. What is this? This is the residual sum of squares when y is regressed on x2. So, what would that be? 1 minus r square y2 times summation yi square, the total sum of squares and the residue arising out of it when y is regressed on x2. Similarly, what is E32i? It is the total sum of squares of x3 and the residue out of it when x3 is regressed on x2. So, 1 minus r square 32 times summation x3i square. Now, if we look at these terms, yi x3i summation divided by, and you have a square root over here because these are the square roots of the variances. So, you have root over summation yi square and also root over summation x3i square. So, that gives us ry3, simple correlation between y and x3. Let us now come to the second term. So, this is yi x2i, and again we have root over yi square, and from here we can factor out 1 root over x2i square. So, that gives us ry2. Finally, if you take a look at x3 x2i, and you have taken out 1 root over x2i. So, 1 root over x2i square remains, and then root over root over x3i square also remains. So, that gives us r23. So, y x3, here you have y square root, here you have x3 square root, y x2i, here you have root over y, and here from here you can get 1 root over x2, whereas what are you left with? 1 root over x2 and 1 root over x3. So, that if you put here you will get r23, and what remains in the denominator is 1 minus r square y2 and 1 minus r square 23. So, that is the simple relation between the partial correlation coefficient between y and x3 given to, and on the right hand side you have the simple correlation coefficients y3, y2, 2, 3. Similarly, if we were to find out the relation between the partial correlation between y and x2, then we would write r y2 dot 3, the partial correlation between y and x2. That means cleansed of variable x3, that would be r y2 minus r y3 r 3.32 divided by 1 minus r square y3, the square root of that, into 1 minus r square 32. Please look at the symmetry, y3.2 y3 minus y2 y2 2 3. So, y2.3 here is y2 minus y3 3 2, and in the denominator you have 1 minus r square y3 when you are cleansing it of 3, here you have 1 minus r square y2 when you are cleansing it of 2, and the other terms are same because r square 3 2 is the same as r square 2 3. So, these two expressions summarize the relation between, the partial correlation between y x3 given x2 and partial correlation between y x2 given x3. Next, we will take a look at the relation between the multiple regression beta 2 and the partial and the regression coefficients arising out of simple regressions. So, we will look at beta 2 hat and how beta 2 hat can be related to simple betas arising out of simple linear regressions. Now, viewers, we will take a look at beta 2 hat and how we can arrive at beta 2 hat from simple regressions. Beta 2 hat from the multiple regression is given by this expression with which by now you are very familiar. But the same expression will come out when we regress pure y, that means y which does not have the effect of x3, only has the effect of x2, on pure x2, that means x2 which does not have the effect of x3. So, you regress pure y on pure x2, that is, this is just like y x x square. So, this is pure y, pure x square. So, just by substituting these values, we will see that we will come out with the same result as we can obtain from the multiple regression. So, that shows the relation between this multiple regression result and equivalent simple regression results. So, what is EY3I? It is y cleansed of x3. So, y minus some coefficient estimated into x3 because y is regressed on x3. That coefficient is like y x3 divide x3 square because y is regressed on x3. Similarly, when we regress x2 on x3, it is x2 cleansed of this estimated part of x2, which estimated part contains this coefficient estimate times x3 because you are regressing x2 on x3. So, this is like some gamma hat times gamma 2 hat times x3, and that is just like we are regressing x2 on x3. So, it is x2 x3 divide x3 square. So, once again very similar to what we have done a few minutes earlier, if you multiply these two terms, then you get y x2, then y x3 divide x3 square, x3 and x2, and again the same thing symmetric, that is x2 x3 divide x3 square into yi x3 symmetric, and plus the last term is the product of these two terms with minus sign, that is again x2 x3 divide x3 square whole square times y x3 times x3i square. So, that last term is minus and minus is plus y x3 x3i square, y x3 x3i square, again x2 x3 divide x3i square, that gives this whole square, and this x3 x3 that gives this x3i square. So, once again viewers, this term and this whole square gets cancelled, and therefore, these two terms get cancelled, and we are left with y x2 y x3 divide x3 square times x2 x3. Now, that denominator, again we are very familiar with this. What is this? From the decomposition of total sum of squares, what this is the error sum of squares when we regress x2 on x3. So, when we regress x2 on x3, what is the error sum of squares? x2i square, that is the total sum of squares because we are regressing x2 on x3. So, what is the residual sum of squares? 1 minus explained sum of squares. So, that is 1 minus r square 2 3. So, r square 2 3 times this was the explained sum of squares, and 1 minus r square 2 3 whole thing multiplied by x2i square is the residual sum of squares. Now, comes the most interesting part. So, this is y x2 divide x2i square sorry. So, that is nothing but beta hat when y is regressed on x2 is we substitute summation y3 ey3 e23, that is this expression we put in the numerator, and the denominator is 1 minus r square 2 3 summation x2i square, which is nothing but the residual sum of square when x2 is regressed on x3. So, that is the residual sum of squares 1 minus r square 2 3 whole thing multiplied by summation x2i square. And the most interesting part is yi x2i divide x2i square is beta hat y2. Then yi x3i divide x3i square is beta hat y3, and finally x2i x3i divide x2i square means x3 is regressed on x2. So, that is beta hat 3 2, and the rest is it remains in the denominator. So, 1 minus r square 2 3. So, beta 2 hat from the multiple regression is equivalent to this expression, which is made up of estimates of beta when you have simple linear regressions, that is beta hat y2, beta hat y3, beta hat 3 2 divide 1 minus r square 2 3. Similarly, if we had repeated this same exercise with beta 3 hat, we would have obtained beta 3 hat is equal to beta hat y3 minus beta hat y2 times beta hat 2 3 divided by 1 minus r square 2 3. r square 2 3 and r square 3 2 are the same. So, that finally shows the relation between the regression coefficient that we obtain from the multiple regression model and components of regression coefficients estimated from simple linear regressions. So, in this module we have taken a detailed look at three things: the relation between simple, partial and multiple correlation coefficients, then simply the relation between partial and simple correlation coefficients, and finally the relation between the regression coefficients obtained from the multiple linear regression model and those obtained from simple linear regression models.